Hi everyone, in this video we're going to be solving logarithmic equations and our main tool is going to be the inverse property again. So our first example is ln of x equals 2. This is similar to an example that you saw in the basic equations video. If we wanted to use the one-to-one property, we'd have to be able to write 2 as ln of something, but it's not obvious how to do that. So instead, we'll use this process called exponentiation. And this is what we're going to use on every single one of these examples. So the way that exponentiation works again is that each side of the equation becomes the exponent, and I have to make it the exponent where the base on each side is the same. So I choose my base to be the same as the base of the log that I'm dealing with. That's going to allow me to apply the inverse property. So I'm going to make my base e. So on the left now I have e to the ln x, and on the right I have e to the 2. So let me just rewrite that. E to the ln x equals e to the 2. But now, by the inverse property, e to the ln, those undo each other, so on the left I'm just left with x, and on the right I can't simplify any further, so I have e to the 2. So we can do the same process in this next example. The next example, we could just apply the one-to-one property, and that would say that 5x minus 1 equals x plus 7, and solve from there. But for the practice, let's use exponentiation. So, to use exponentiation, each of these will become the exponent, and I choose my base to be the same as the base of the log. This is log base 3, so I'm going to put 3 as the base, and those become exponents, so we'll rewrite it. 3 to the log base 3 of 5x minus 1 equals 3 to the log base 3 of x plus 7. So by the inverse property, 3 to the log base 3, everything goes away except the exponent. So I'll have 5x minus 1. Same thing on the right. I'm left with just the exponent, which is x plus 7. And now I can solve. So in order to solve this, I'll bring all the x's to one side and everything else to the other. So I get 4x equals 8, and that means x equals 2. Okay, so let's do a slightly more complicated example now. I'm trying to solve for x, but there's all this extra junk. And so what I want to do is first solve for ln x. So that will give me an equation like this one. I'll have ln of x equals blah. And then second, I'll exponentiate. So I'll e both sides. So let's solve for ln of x. That just means get it by itself. So what I do first is bring over that 5. So I'll have 2 ln x equals 4 minus 5, which is minus 1. Then I'm going to divide both sides by 2. So I'll have ln x equals minus a half. So now I have an equation like my first one. So this is the stage where I exponentiate. Or e both sides. So I'll get e to the ln x equals e to the minus a half, but e to the ln x, oops, sorry about that, e to the ln x, by the inverse property, that's just x, so x equals e to the minus a half. So first isolate the log term and then exponentiate. We'll do another one. So again, first isolate log term. Second, exponentiate. So here's my log term. I need to get it by itself. So I need to divide both sides by 2. So I'll end up with log base 5 of 3x equals 4 over 2, which is just 2. Next, I'm supposed to exponentiate. So these will become exponents, and I choose my base to be the same as the base of my log. So I'll end up with 5 and 5 as my bases. And my exponents will be log base 5 of 3 to the x and 2. So then by the inverse property, 5 log base 5 of 3x just leaves me with 3x, and 5 squared is 25. So here to here was inverse. And now I have to do one more step, which is just to solve for x. And so I do that by dividing both sides by 3. And I end up with x equals 25 over 3. So it's not so bad. Okay, this last example is a little bit tricky because I have these 2 log terms and the 2. So I can't isolate a single log term as of right now. But what I can do is I can use properties of logs to condense. That way I have just a single log term. So if I have log of 5x plus log of x minus 1, the product property tells me that this is the same as log of 5x times x minus 1. And the other side of the equation stays the same. So here to here, I use the product property in order to condense. My second step now is that I have something like log of blah equals a number. So just like in this last example, I'll need to exponentiate. And I choose my base to be the same as the base of the log. So when I write log without a base, that means log base 10. So 10 to each of these powers. So I'll have 10 to the log of all this stuff equals 10 to the 2. By the inverse property, now I have just the exponent left on the left because 10 to the log base 10 of an exponent just leaves me with that exponent. So I have 5x times x minus 1 equals 100. And now I'm going to need to solve for x. I used pink for that before. And this is just a quadratic equation. So I have 5x squared minus 5x minus 100 equals 0. Divide everything through by 5, gives me 5x squared minus x minus 20 equals 0. Factor this, x minus 5 times x plus 4 equals 0. And that tells me that x either equals 5 or x equals negative 4. But I want to check these back into the original equation. When I actually plug in 5 here, I get log of 25 plus log of 4 equals 2, and that's good. This is a solution. But if I plug in negative 4, then I'm taking the log of a negative number. So let's see what happens if I do log of 5 times negative 4 is negative 20 plus log of x minus minus 4 minus 1, which is negative 5. And I get a non-real answer. That's because if you remember that if I try to graph the log function, my domain is all positive numbers, so I can't be plugging in negatives. The solution x equals negative 4 would lead me to plugging in negatives, so in fact, it's not a solution. Our only solution to this equation is x equals 5. So be a little bit careful when you come up with your solutions and make sure that they're actually in the domain of the log function. So those are all the examples I have for you right now. The key things to remember are that in all of these examples where we're trying to solve a logarithmic equation, we're going to want to isolate the log term or just get a single log term. That way we can exponentiate, and then we may have to do a couple extra steps to solve for x. So I hope that this helped, and good luck with the web work.